Okay, so yesterday we had a laboratory. And we talked about the corpus callosum. What does the corpus callosum do?
So the connection between the two hemispheres.
It connects the two hemispheres together. I'm right-handed, so which side of my brain controls my right hand? Okay. Where is language in my brain? Left side. Okay, I'm going to show you a video about a person getting their brain stimulated through the skull with a device called a transcranial magnetic stimulator.
Transcranial kablingi di jika ta kujin che ta in level at the low tanchero ene ta di tujijures ta di gune level nalola data ene level at kujin te worda ta digi ne nyentun jiten yosigdo.
So imagine this is someone's skull.
And
this is their brain inside. We have a device that can generate a magnetic field that will disrupt the activity of the neurons right underneath it in one location. I said disrupt, but I meant activate and disrupt. Activate and disrupt. So if I took that device and I put it over your skull, where your hand area is for moving your hand, and I turned it on, I activate it, click, 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 click. What do you think your hand would do?
He will shake his hand.
Yeah, click. Your hand will move even though you didn't tell it to. It's not because you're stimulating the muscles in the hand, it's because you're stimulating the neurons that control the hand. We can use a device like this to test different parts of the brain. And I'm going to show you a movie of a person having his speech area activated so he can't talk. Just transiently can't talk. He's going to be saying a common children's rhyme, Humpty Dumpty. And when you hear the clicking, click, 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 they've activated the stimulator, and he'll, like that, won't be able to speak.
쿠네 단다 주지드 그 파르심베네 컵라 가르스나 쿠 기체힘에도 버차도 그랬어. 담보이네 쉐드 당기라 바로 될라에네 단다 주지드 가르데 삼바에네 쿠 바로 될라 체두고 서와다.
I'm Roger Highfield. I'm the science editor of the Daily Telegraph. Now, words mean everything to me, but now I'm going to have the speech area of my brain turned off with a giant magnet. Humpty Dumpty sat on a wall. Humpty Dumpty had a great fall. All the king's horses and all the king's men couldn't put Humpty together again. Humpty Dumpty sat on a wall. Humpty Dumpty had a great fall. All the king's horses and all the king's men couldn't put Humpty together again.
That may have looked like a strange party trick, but it's actually part of a serious research project conducted by Prof Vince Walsh in a basement lab at the Institute of Cognitive Neuroscience in London. He's using electrical and magnetic brain stimulation to understand the most complex known object in the universe and how to treat conditions such as migraine and stroke. Just to show the power of the magnetic fields passing through my scalp, and that this wasn't a trick, this is what it did to our videotape, even though it was positioned a few meters away.
Star Trekking. Yeah, very left eyebrow twitch.
It's hard to see because of the interference, but here I could still sing a nursery rhyme, even when he disabled my language centre, because singing depends on the other.
So what he's going to show you now is that he can sing the rhyme, Humpty Dumpty, because singing is in a different place as talking.
양데 가서를 단투고레스 양 제코랑기 양주로 양데 단투고레스 임바이나 단다 칙디기 들랍투고 말레스 카레스나타 양 양라 단전체니 양 땅에라 단전체니 레베 체히다 네 케이라 단전체니 레베 체히 로어레스.
In rare cases, people might have a small lesion in the area used for talking, and they can't talk, but they can still sing. If they say, "Hi, how are you? It's such a lovely day." You know, they can sing it, but they can't say, "Hi, how are you? It's such a lovely day."
저선다에네 가서를 계기 다 레빈 제시델라 죽균들이 쇼르체 계제히메도 차와 있나요? 네, 다네 양데네 땅 투견들이 미용 네바든지 요레스로 다 콜라이네 직 셴예진직 땅데 선바로 코디 제두체체네 양데 땅 투그레스 뭐네 칙들 랍투 말레스.
Because singing depends on the other side of the brain.
Okay. Humpty Dumpty sat on the wall. Humpty Dumpty had a great fall. All the king's horses and all the king's men couldn't put Humpty together again.
I felt a bit apprehensive during this intriguing demonstration, but Professor Walsh thinks nothing of tinkering with his own brain for the sake of science.
Jack and Jill went up the that's great.
As researchers from around the world are about to gather to discuss the latest results, he told me about the remarkable potential of brain stimulation.
Okay, so you all saw that the research scientist, when his language area was stimulated, he couldn't talk.
저선다에네 당기 냠시바디네 거의 주체 파티 참바 계기 단다 내지도 아딜라네 데스 샤드 참바코 계적힘에도 차루도스.
Sometimes people have a tumor in their brain and it has to be removed.
저선 삼삼라다에네 미 레벤알로 단다 10 시그로 단다 가르소다 10 시그로 10 든지 총체 네 다디 꼬고야 든지 차고레스 샤주단치 꼬고야 든지 차고레스 10 시그로 아딜라.
Everybody's brain is a little bit different.
저선다에네 미 가르소그레 문도 레바 문도 레스미솔라 this dogmaris.
So in Paul and me and our translator and our TA, all of our language areas in a little bit of different places.
저선다 나다 따네 미 바로 들어와 있나 그랬으나 계획이 단다기 내주라 계획을 단순히 내데 테스트 로어스 요소도 테스트 로어스.
So if the surgeon has to remove part of the brain because of the tumor and it's near the language area, he has to find where that language area is to make sure he doesn't touch it, because you only have one.
자산다는 텐데 갈수록 다 레베나로 자식 가와이면데 그 야구 섭섭체나 마더라. 근데 계획이 단다 내디네 자식 축구샤바는 그 기자 힘에도 자루 그래. 자산 그 샤주 단데 삼바 담보 계획이 내데 가와 렌도에네 두스 야구 딱 그래서 저다체 그래서 다 디젤라 코시네 섭섭체네 두스 텐데 고 그래서
What would happen if the surgeon took out the language area or damaged it?
딱 기존에 계획이 내디네 그 샤주 단체 때 견당바이나 같이 그래서 계획이 제샤 그래서 he'll forget the language.
He wouldn't be able to speak.
저런데 계속 힘에도 배차로 그러왔어.
Would they be able to sing?
양땅 두그려했어.
Maybe they could chant too.
저런데 덤바연던 투사랬어.
Okay, I'll show just a short video here.
I just want water. I first heard about the surgery where I would have to be awake about a month ago.
It's not a matter of being awake or not. It's just the whole thing about having surgery of the brain, period. It's going to be like the hardest thing.
Very nervous. I'm a nervous guy.
It's going to be the longest 4 hours.
This girl is going to have neurosurgery done.
저런데 부모들이네
You're not going to be a teddy bear. What am I going to do with this thing?
Because she has a tumor in her brain.
레베나로 10 years 그라.
Right, baby.
What?
A few more hours, it'll be all over.
Thank God, I'm tired.
All right.
So how do you guys all feel?
Well, it should be over, that's all.
If they would let me scrub up, I would love to come in the operating room. I would love it.
The idea is to take out the tumor and leave the brains behind.
It's sort of a misnomer. You're not awake for the entire procedure. For most of the surgery, you're going to be quite deeply sedated, so that you.
But to map the language area, she has to be awake during the surgery.
저단다에 단다기 계획이 내데 그 섭자서라 그 샤주기린라 그디 가서 그래. 니세데 그랬다네. 니세데 가지고 그랬다.
The art part of this is tailoring those medications to the point where the patient is sufficiently sedated that they tolerate the procedure.
Time out. This is Brittany Capone. She has a left posterior temporal tumor. Everybody agree on the left side? Yep.
Okay, so the girl is awake. And her skull is open. And they ask her questions. Like say words that start with B. And then they stimulate different parts of the brain. And when they stimulate the parts of the brain for language, she can't talk.
Let's
see if they show a picture. There, they're stimulating. This is the picture of the brain. This is the girl's brain right here. And this is a cutting device, but also they have a stimulating device. And they just stimulate and find exactly where language area is. Once they find the language area, they put a little piece of paper on it to label it, and then they stay away from it.
shogu jarche de la ta japsha gres jazan ko shaju tande samba di la kin tugju mares urta
in New York City.
And then after the surgery, now she can talk. She's okay. That's the scar from the surgery there. Okay, any questions about that?
Di tola chua
the microanjige lava dinde jikjine katune mi kingudo dinde choda lava de katune dargodo
lava dargodo as
koen arashinji dinde jigede de garede
arashinji dinde jigdos. So there are some people even without stimulating any brain area they're constantly shaking their hands.
Yes, tremor.
How does that happen?
Okay, so the question is, some people have tremor. What's the mechanism of that? Anybody have an idea?
So there must be some impairment in the way signal is traveled through neuron. What we talked about yesterday, the action potential, the ions coming in, going out, all these processes might be impaired.
Yep. Good. So the circuit that moves your hand, the neural circuit moving your hand, is impaired.
Lagba kujutan dengengi ta logi korlam jura logi korlam de ne karsurta kön şuruyuz.
And it's spontaneously sending signals to move your hand even though you're not telling it to.
Chazanda ene sosu lagba tango samche dende datin dende matang na ra living mone matang na ya karsna ko sharim de line datin dende jor dugures. Chazan jorche ne lagba dus ranshingi kujuk da ranshingi kujuk dugurta. So he was asking the question, what could be the cause of this
tremor?
Tremor.
Yeah, so the neural systems that control your hand are having spontaneous activity that tell it to move even though you're not telling it to move.
저선다 스승문에디 구제탄셔세 가르스고름 랍메나야 로 아니 완자 타봉다 완자 말라디기로 완자 말라디기다 랑구기 통네스고로 랑구기 통네다 딜라 다든리 땅체 네 구제탄고레스 라바드.
Can anybody think of another example of that? Another example of a body part moving or your brain telling it to move when you're not telling it to?
저선다 네 스스 구제탄셔세 말랍나야다 네 스스 랑구기 통네 구제 가르스고르 잡데 기타 네 피친 샴바지 샤바이나. So the example was sometimes you have some jerk motion during your sleep. Sometimes you, for example, the knee jerk. Knee jerk is one example when you're not telling your leg to move, but your move just moves spontaneously.
Mm-hmm. I can tell you one that's very common that you all think about all the time, but you never pay attention to unless you mean to, and that's breathing.
저단다에는 남경안서 가서 그랬다에는 지금 랑구기 토네 최대와 간식랑 안서시라 도난 되게 메시지다에는 자와주 레스티카르스나 먼저 로야 들어왔어. 이게 로야.
If I tell you to take a breath, you can do it voluntarily.
저선다 기란서 우탄쇼랍데 선바에네 다 소소 가서 우리 균로 예배 토네다 우탄 투그레스.
But if you're not paying attention, you will breathe to keep your breath going in and out, even though you're not thinking about it.
임바이나다 소소 삼로 마땅베 삼로 땅 무고에 토네다 양안저 랑구기 토네 탄 투그레스.
That's an example of something that has both involuntary control and voluntary control.
저단다 디네 랑구기 토네 탄투베 당진다 ene rangugi tangzinda rangu mayimbi tangzingita nika yongchoye pechinjires.
So when the hand shakes like this, that's an involuntary action.
당연히 라바 쿠란 두스 구jet단데 가스나 rangugi 톤에 연거레스 근로 맵이 톤에.
And then when you reach for something, even though your hands shake, that's voluntary action.
단 라바 다르기 야네 페나 잘라질라 두스 스미아주라 근로 여베 톤에 두스 스미아주라. 가스나 당에 rangu mayim바다 근로 여베 근데 구jet치 차데고레스.
Okay, so today we're going to talk about action potentials, which are the major mechanism by which neurons communicate in the brain.
저단다 ene 드링 안서 레직 톱체세야 돼 콜라 장기스 저단 레직 톱체세야 돼 ene 원자 처본 치지라 ene 드와서 다 ene 드투체야단 드투체야겠다 ene 말라 시름기다 말라 넣어버렸어.
So after this lecture, you should understand why we have action potentials.
저단다 ene 롭트디기 ene 타마델란 안서 레직 톱체 연구에 겸센다 다 그바 계란서 하고 그랬어.
How action potentials are generated with ions.
저단다 ene 게들 딘리 라테네 ene 레직 톱체데 간디치네 중구에메 되지 그랬어.
And yesterday I talked about what kind of fish that's poisonous.
가장 먼저 네 냐치 콜라 키치히엠바 네 둑둑 요기 냐치 네 가르레 냐데 puffers 에드라 puffs 디가 나치 땅고 this 감보나시 차려야 될라스구라.
Why is it poisonous?
저단들라 둑 가르치는 둑 요레스. 가르치는 둑 요레스 콜라. So like self-defense.
But how is it? What's the mechanism by which it's poisonous?
저단다 ene ku 둑 차에게다 ene 콜라 든데 둑디 ene 냥가 차에게다 ene rollu rotan데 근데 치레스다 ene 간데 오치다 ene 둑 차고. So it blocks activity of neurons.
It blocks activity of neurons. So we're going to talk about the mechanism of that later on today.
저단다 디기 ene 다 rollu rota ene 다 디 무트네 장게 인식도 디 간디치 코 가게 메데.
Who recognizes this? What is this?
딘 파르텐 타데 참바 ene 니마 통뇨니 다 무신이 스유스.
What is it?
가르레. 도구로와. Reflex.
It's a reflex. Who can say it in English? What is it in English? Knee-jerk reflex.
Knee-jerk reflex. 다인데 뼈목이 해부 도구스기다.
Knee-jerk reflex.
뼈목이 해부 도구는 줄라.
Okay, the knee-jerk reflex is a very simple loop between stretch receptors, the spinal cord, motor neurons, and muscle.
저단다 ene 뼈목이 해부 도구스야 되가르스나 ene 단다 경시 저렇게 게다 넬렘바다 다는 신에 경바다 다는 신다 ene and the last one was
muscle. Go to the muscle.
This one?
Yeah, motor neuron.
Good you once a taponda this digi ta parula yongeta korlam tab deuchi res urta.
How far is it from your knee to your spinal cord?
저단다 ene 뼈문에 경바 버도 ene 타를 res. 타를 장사가 저 check out half meter.
Half meter, about that. How can you send a signal half a meter?
저단다 ene meter checkasne 다친 땅 건데 참 간디치 다친 땅 그래스 간디치 땅 거래. Lodel, Zedul, Z, Lodel Z, through electrical and chemical signals.
This is electrical, and this is chemical. The synapse is chemical. So you have to use electrical signals. It's like a telegraph.
저단다 ene logi datin tangores ene dinashere karsa ta ene telegraphs tigala ta anzo yitin sigre karsa lungting ta yita jda lungting.
Who can explain to me how a telegraph works?
저단다 ene telegraph se ade ene kandichiku chelu chatan de kandichi ima haku yes. Some say through internet, some say
no, telegraph is ancient, 200 years ago.
Telegraph said that Ningbarda, and so the Lowlet and the kind of matter conla. Condition younger, Datin Imba Kanshila, Datin Girichita.
What do they say? They don't know telegraph? Okay.
Angi through digits, numbers,
pulses.
Then parza tangora. Kuba Guinness through wire.
Yep. So. In the old days,
there's a receptor on the other side,
yes.
receiver.
Okay, in the old days, before telephone,
they
used to send signals by telegraph, and they would have a sender and a receiver and a wire in between.
And the
sender would tap and make an electrical connection. And the receiver would hear the tapping because his device would tap at the same time.
And the
So they came up with a code. They agreed on a code called Morse code. And the agreed upon code was such that a certain type of tapping meant one letter and a certain type of tapping meant another letter.
And
so the receiver would sit there and he would hear tap 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 tap, and he would change that code into the words, the letters that made words for the message. Your nervous system does exactly the same thing. If I touch your skin, you feel the touch, but your nervous system only hears pop 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 pop. And then your brain turns that message back into the feeling of the touch on your skin. Okay, in the nervous system, each one of those pop, 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 those are action potentials.
저선다 인데 원자 말라기는 단다 파르덤 딘디도 디 카르스나 파르덤 레레레 카르스나 코 레죽 덮쳐서 드레스.
So when I tap on your knee, the receptors here fire action potentials, and they tell the neuron that the knee has been tapped. They generate new activity, pop, 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 pop. And that tells your muscle to contract, and you move your leg.
저선다 인게 지난 게 뿜을 다 셔름들 슈디 삼바 에네 다 셔름디기 에네 레죽 덮쳐 펭고레스 다 레죽 덮쳐 디스펜체 가르스나 양 원자 토분 셴바 김바기나 원자 토분 셴바 칠라 땅체 디기야 에네 셴바 칠라 땅양 디기야 추 가르스나 셔름기 촐라 양 원자 가르스 버다 파르덥든리 둥그레스.
Is there any question about that?
디기 톨라 투와 레바기 파르덥 디기딜라고 로드 치고르다 리시게 오르다 다네 파르덥 딘디 치요스나 다디기네 딘디 땡고르다 세노치다 리시게 오르다 파르덥 니숨 딘디 요바이나 에네 다디기 이기 까츠 거 요바체 나 파르덥 숨 딘디 요다 시 딘디 요바이나 카스 다다가 비준 삼르다
레 지다 레바게 된 파르덥 지 요바데 레바게 하고 요라
레데 파르덥 마도 랭고 마로. So the brain receives only the pulses. Up to the brain, it's not in the form of any message, right? Then the brain just interprets those pulses as something meaningful, right?
Yes, and that's a very, very big problem we have in neuroscience, because we believe the brain gives rise to consciousness, but we know that the brain has no... The brain doesn't operate through thoughts, it operates through pulses. Pop, 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 pop. Billions and billions of pulses. Pop, 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 pop.
저선다 이네 디 원자 세미기 나오네 지단 강인 로지 차디 그래서 지단 먼저 가서 그래 남시세야 돼 남버 시바세야 돼 먼저 다 레베기 자와지 뭐 문제 치고 그래 다 레베기 가르스나 고 레야 돼 바르도 치고 마도 랭고 말했어 레바버도 저래야 주라 레바버도 저래야 돼 먼저 원자 타봉균에 저래야 돼 가르스나 바르도 브라레스 바르도 미진치 저거래 다 디기네 가르스나 레바기 텔라타 로드 갭 네 따티 된다요 바치서 거다
안에 단나디 파르도 딜라네 로와 근데 방서 루슬레티 메다나 다나디 데두지요로다 베나 잠보레지 수부레지 스테지요 디에다 파르도 균 하고 그러스. So the skin receptors also send the certain pattern of pulses, and through which the brain interprets it as a like rough sensation or smooth sensation. Is it the same?
Yes. So
roughness and smoothness.
There are two different ways for the brain to know information. One is the pattern of the pulses. If it's fast, or if it's slow, pop, 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 pop.
다이네 레베기네 코 차틴데네 랭기 다이네 차틴데 코 로드 제단기 다이네 탈럼니르 스틱데 가르스나 코 파르덥디게네 드럼 간데지 두세 드럼 스틱한다 근데 파르덥디 교보쇼지 바이나 교보쇼지 요바다 야마나 파르덥디 대우 다드니지 요바다 디 드럼 주라 드럼 디기 토네야 하고 그래.
And the other way is by which receptor is stimulated.
니바데 가르스나 코 넬렘바 가기 전에 연구도 써야 돼. 넬렘바 가와네 연구도 넬렘바이 네다 박박이 넬렘바레면도 네 렌도 야마나 넬렘바 샴바지렌드라. 그래서 넬렘바 가와기 전에 연구도 써야 돼야. 답은 니바드레스.
If a nerve from your eye fires pop 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 pop, you see. If a nerve from your ear goes pop pop pop, you hear. If a nerve from your skin goes pop pop pop, you feel.
저선다 코인에 미기 초원에 따이네 바르덥든지 따 드릉 예전지 연구해 봐이나 디면서 통통 두바체 에네 다기 암조기 초원에 드름 찍바찍이 한든지 랩드 삼바 코 가르스나 따디네 다르셔서 지래 다는 신간 저 박박간라도 양 박박이네 원자 접근 되기디야 파르덤 예전 주tun데 삼바 직과직견 드름 직과직견 tun데 삼바야 어디 리자르샤 하세요부터라 그 저산도 드름기 톤에 하고야 다는 신 원자 넬림바기 가와기 촌의 연구도 어디기 톤에 하고
That's something you learn as a baby. That's something you learn as a baby as you grow up. You learn from birth on up.
저한테 먼저 보고 준중내 땅에 검식 장대바 보고 준중내 손제 땅에 먼저 장대바 차고레스 디기 좋단데.
Okay. When you're very young, this is an important concept. When you're developing, when your brain is developing, it's learning to see, it's learning to hear, it's learning to feel, as well as learning to move.
저는 경영이 레바데네 기빌 도데 참바타네 담보 춘데네 기빌 도데 참바 코네 통야당 퇴야당네 레기아데네 장고레스 정말 근데지 통구 근데지 퇴부면서 정말 장고레스.
Who knows what a newborn baby likes to look at?
Likes to look at. 다이네 부춘중게 있는 가서 그렇다. 따야 가고 요사네 그래 뭐 하고 됐어. 즉 통야 따야 가고 요사. Cartoon movies, cartoons.
No, newborn, little baby, just born.
단단한 키스르교네 보고. 아마 mother,
and they're born wanting to focus about this far away at the mother's face because the mother holds the baby, and this is how far away the baby's face is from the mother's face.
Wanting to.
They are innately attracted to look at mother's face at this distance.
다코네 보고 단단한 키스르교 보고 되가스나 따 란중 따네 가서 란중기 톤에 따 양세 딘리치길라 네 소소 아마데 통투바서 그래 통야기 두바이가 딘리치 차도 그래 통야기 따네 둠바이가 딘리치 차도 그래 란중기 톤에.
They have to learn to see cartoons over years. They have to learn to understand what a cartoon is. They don't even see it as a newborn baby, but over time they can learn, and as a child they can watch cartoons.
저는 그 카툰 세계 따네 딘리 로닝 군인들도 저는 디네 그 따야라 군수 장고레스 담보 기도 상반에 가야 하고 말했지. 따네 림베 그 장체네 따네 카툰 되게 따체 그 된다 거에 기준을 차고서라
로균이와 로균 대가스리에 치고 와라체 치 강나도도 아니디 로균 대가스리에 니까 가스리
만다르스. So the two currents that are coming from the stretch muscle and then going back to the motor muscle, are they different types of currents?
They're nerves. Yeah, these are different. This is a sensory input and this is a motor output, and they have some differences.
비 원자 타본 문제와 리스크니로 원자 타본 문제와치 단다 강마디 바이나에 단다기 왕처르기 따에네 낭댕스 그래 낭댕 원자 타본스 그래 낭댕 원자 타본다 에네 오게데 가르스는 구규기 따 치댕 원자 타본스 그래 치르댕에다 낭라댕에다 치르댕에다.
This curve here, this curve is an excitatory curve and makes this muscle contract. This one has an extra neuron which inhibits the neuron and makes this muscle relax.
다에네 강마디 디 마르보니도 마르보 강마디 가르스나 에네 나르랑기 에네 원자 타본 차데고레스 저장코 딜라트체 코 나르랑 체그레 에네 오마디 바이나 가르스나 탄다 강네 연주 다데 가르스나 원자 타본 딜라트 디 원자 타본 디 가르스나 마르보 오마디 가르치르스나 나르듬 체그레스 기도 나르듬 체체 에네 샤름데네 쿰그레스 쿰그레스.
So when I move my leg, if I go like this, I have to contract this muscle and relax this muscle.
저단딱 니 감바두스 구제탄데 삼바 에네 샤름 강마데 경체 샤름 오마데네 쿰고레스.
So what happens when I put my arm like this? What does this muscle do?
다 저단 라바두스 구제탄데 삼바 에네 샤름 강마디 가르쳐 그래. 꿈꾸라. Contract.
Yes. What does this muscle do?
저는 목마디 가르쳐 그래. Release. Relax.
Okay. What if I go like that? What happens?
The lower muscle has to be contracted and the upper muscle has to be really relaxed.
Good. Oh, who can tell me what this is? What's this a picture of? It's in the body right here. What is it?
So it's translated in Tibetan. So sciatic nerve.
Sciatic nerve. Okay. This is a nerve bundle. Every part of your body receives nerves. The only parts that don't receive a nerve, maybe your hair. You're outside of your fingernails. Okay. How many axons in this nerve? In this nerve, how many axons?
Some three. Many.
Many. You have to send an axon to every part of your leg, your toes, the bottom of your foot, the back of your leg. All of this has to have axon for each little part. If we take that nerve and we cut it in half and we look at it like this, these are the axons inside that nerve. So nerve is made of many, many, many axons. And each axon goes to a different part of your body. So remember we did the 2-point discrimination? Which area do you think has more axons per unit area, my lip or my back?
Lips.
Lip. You can have very good sensitivity here. You can distinguish between points that are very close together. That means the axons are very dense. About 80 years ago, these two investigators discovered the pulses of the axons. The pop 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 pop. This is a visualization of one pop, one pulse, one action potential. This is time and this is voltage.
다이네 테틱라 가르스나 간저 뒤체 숑틱라 가르스나 간저 월세 템고라.
Does anybody know how long this lasts in time?
저단다 디기 뒤용 가지 고르기 요면 하고 요베스 파르답치라 뒤용 가지 고르기 요면. No.
It's 1 millisecond. 1 millisecond.
저단다에는 millisecond 찍어요. millisecond 찍스티가 second 찍 동부 찍돈 담발라 땅이 차지로 동차지로 네 가르쳐 동차지로 가르쳐기 동차지로.
So if it's 1 millisecond long, what's the largest number of action potentials we could have in 1 second?
저단다 기제네 파르답치기네 뒤인데네 가르쳐기 동차지기 마이나 가르쳐지기 나올라 에는 간서 파르답 가지 서도사래. 1,000. So the code on your axons from your knee to your spinal cord must go between 1 hertz, 1 per second, and 1,000 times per second. 1,000 times per second. Code.
The code, the firing rate. Like 1 second, pop, 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 2 hertz, pop, 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 3 hertz, pop, 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 pop.
다에네 저단코네 단다게 파르답기 단다게 다지요라 다 딕단지요라 다 딕단데 가르스나다 세긴치기 나올라 찍네 네다 찍동 파르도드니 데체 든디치 칸라 요고레스다 데체.
I have an app. I'll show you later what 1,000 hertz sounds like. It's on my phone.
데체 찍동 세데 간디치기메 찍가르스고레 땡야치 요세기도.
So how did they discover this action potential? They discovered it by recording inside one axon.
다이네 디 파르답데 군저 간디지 체제 투비어레서 아이나 에네 군저 단다 다키츠든 든디기 나올레 체제레스기도.
Normally axons are very, very small.
균딘 라인에 다키츠든 데페 타모슈에레스 탑탑슈에레스.
This scale is 20 microns, 20 millionths of a meter.
저단데 디기 빠르디기 체득데 가츠레스나이네 마이크로미터스 디가라는저 미터씩 사이즈라 땅베 동부 사이즈라 땅베 차지로와 저단다 든디 체 타모든데 이랬다.
So each one of these axons is about less than 10 microns in size.
저단다에네 다기 차트 레레기 단다 bom체지라 bom르데 가츠드스나 마이크론 10 micron chuma domandus micron chustigala in metric size latam tumbu size latam chajira.
That's much smaller than one hair.
So then in it tagi bomse le kya in chuma tap bundis chagores.
So if I asked you to put a recording electrode inside one of these tiny axons, it would be impossible. Until modern times, it was impossible.
저단다에는 간저 로기 다 투체든지 쭉제 간저 체제에게 투체든지 디난 쭉바이나 간저 다에네 쭉 못바치 차도 그래 사장 타타네로 탑탑.
What kind of animal is this? What animal?
디네 심정 가르레스.
It says on it,
그래 신세더라.
Squid. It says squid.
서브레슨.
I can't say it. Now I understand how hard English is for you. Okay, a squid has a giant axon, very large axon. Who knows what a squid does when it's threatened?
So it'll release some poison or something. So it'll move away or avoid or.
That's what I'm looking for. It moves away. How does it move away?
So it has some tail or something.
It moves away by contracting its whole body like that and squirting water out.
타코 간데지 투고르스나 코 수부 간산도 꿈고레스로 수부 간산 꿈체 에네 파기 굽스고레. So this is like a
jet, like a
through its mouth or
through opening here.
다딜라 코 네 부가치에서로 부가딜 균에 코추 흉충부 슈지파 비자탄 거였다. 추 흉충부 비자탄데 참바 코 가르스나 파 도셔.
I believe the opening's here.
다딜라 에네 코 가르소르다 부군 어디다 가르소 카드 어딘지 주의사르다.
And when it contracts suddenly and squirts water out, it moves rapidly to the other direction.
저는 수복관산도 꿈디 삼바 가르치고 그랬으나 추배 흉충부파 찌르고 있어라. 추 흉충부 찌르지 에네파 비자탄데 삼바에네 수복관산에 수용거라.
This axon controls that behavior.
저는 나기 같은 니기 가르치나 단다기 기름들라 단전체고레스.
And to help the squid do it very quickly, the axon is very large.
저선다 들린다베네 레가데네 교부슈 체고데 참바에네 나기 같은데 침보면에 연구 말했어. 저선 침보 연구에 김선들레스.
Because the axon is very large, it could be 1 millimeter in size, 100 times bigger than normal axons, 100 times bigger.
저선다에네 나기 같은데 에네 가르스나 범체데 가서 열스나. So you're talking about the diameter, right?
Diameter. This.
저선다 범체데 가서 열스나 에네 밀리미터 칙 열스라 밀리미터 칙. 다 균댕기 다 나기 같은데 답갸기 에네 bomba 열스기도.
Because it's so large, these two investigators were able to put a piece of electrode inside the axon. That's what this is, an electrode inside the axon.
저선다 에네 딘리르베 나기 같은 침보 여대가 bombo 여대가 가르스나 디 나로라 단다기 로기 에네 체제기 다 주제딘데 나로 탄투비 열스. 저선디 파르데가 땡기도 디 가르스나 에네 로 체제기 주제디체.
And that allowed them to record the action potential. Any questions about that?
So did they like take an axon and put it on a microscope, or did they just directly put the electrode inside this body?
I have a movie that we can show you. Okay, these are different types of squid.
So perhaps it's not surprising that it took a long time for scientists to discover that there are fundamental similarities between the nervous systems of cephalopods and vertebrates.
This is a squid, and
Yet it was the
you'll see in a minute example of how it can squeeze its body to escape.
The breakthrough concerned the nerves that control the contraction of the mantle muscles used in jet propulsion.
Okay, so they're going to take a squid out. They're going to take a squid out, and it's going to squirt all the water out of his body to try and escape. There's a squid. See all the water come out?
In the mid-1930s, the British zoologist Professor
And now the squid is dead, but they can dissect, open the part of the body that contracts. This is the axon.
They could not be similarity to surrounding nerve fibers. Young thought they must be single neurons, giant axons, that transmitted nerve
10 times,
from a concentration
100 times bigger, no, maybe 10 times bigger than a hair. These are the axons. If they stimulate the axon, you see the muscle move.
Okay. These were indeed giant.
And now he's going to take scissors and he's going to cut and pull out the axon.
지난다 그 단다 나게 저런데 그 장직이
This is the single axon right there.
어디 나게 저런 강치이다. 든리 친구다.
This is the axon.
나게 저런 치이다디.
The intracellular contents of the giant axon.
You can't see it, but it's right there. There's a little axon right here.
Sodium ions were more concentrated
axon.
And potassium ions more
They
concentrated.
can measure the contents of the axon. That's how we know what's in it.
By refilling the
Here's a picture of the axon.
어디 나게 저런데 이빠르데스. 나게 저런 나올라인에 다 실고 가려는데 세제 투그레스 실수 가려는데.
Okay, and now they're going to put an electrode inside the axon. This is the axon.
지난달에 나게 저런 나올라던다 이 로체지 로기 제체되네 투그레스 단다.
So he's going to put this piece of glass inside the axon.
지난달 단다 이 로기 제체되가 스나코 실기 소기든지 그래서 지난달 나올었던 그래서.
He uses a manipulator, and then he ties a string. Literally ties a string around to hold the glass in place. Okay, and now they can record the axon. This is the electrode.
But the formation of the nerve impulse.
When they stimulate the axon, the muscle can move.
With any of the electrical measuring devices. It wasn't until the 1950s, following the wartime.
Now they're recording the action potential.
Cathode ray Scientists found that the nerve impulse was transmitted as a characteristic wave of electrical potential, and that this all or nothing action potential.
So axon means one one
fiber.
One fiber of axon, or does it mean a bundle of fibers?
A bundle, an axon is one, a nerve is many.
지난달에 당일 때 세시치고 그들아 먼저 남기 완자 랍돼야 돼 먼저 완자 잡은 거 거고 말다 완자 스팅하나 먼저 나게 잡은 거 거고 나게 잡은 게 차과 찍라 완자 세버다. 지난달 나게 잡은 게 망고치 뜻 냠도 차과 찍라다 완자 세버. nerves이다. 저는 이제 nerves 해야 되는 저 완자체 neurons 해야 되는 저 완자 타봉스 유르다. 저는 완자 타봉데 노르게요 말에.
So we talked about the sciatic nerve.
저는 단단한 저 뇌를 완자 해야 될 걸로 자인바.
In your leg that has many axons, maybe a million axons.
지난달에 단다 강바강라 뇌를 완자딜 차샤바는 나로라다 네 다게스를 망보쇼이래 다 사회 망보요래서 다 차과찍을도.
Okay. Now let's talk about what we learned yesterday.
다 가상한서 장설교대 연결치 결십체 바이나.
What generates the membrane potential?
다 기목이 덕체 튜니스레스. 기목이 덕체 튜니스레스. 튜니스레스. 가리기 원기형 거레스 기목이 덕체데. 가르디 박체. So concentration gradient.
Concentration gradient. What ion is most concentrated inside the neuron?
다이네 원자 저봉이 나로라 이네 게들 가기 가르세 토슈 차고레스. 가르세 토슈 가르레. Potassium.
Potassium, great. What's outside the neuron?
네, 원자 저봉이 첼로라인에 게들 가기 가르세 토슈레. 이제
Sodium. Which way does potassium want to move because of the concentration gradient?
가르디 서버기 왕기스 네 두스 가보드 네 초가이 촐라 도고레스 촐로도 out.
Okay, out. And when it moves out, what happens to the membrane potential?
ene 두스까고 촐로 텐데 참바 ene 기목이 덥질 기로 가르도 그랬어. More negative, more negative.
Yes, because of these anions, it becomes more negative. So when potassium goes out, it becomes more negative.
저단다 ene 코 나로라 단다기 게들 모든데요로 게들 모든데요 와선자 완자 타본 나로데 그래서 모시체와 차체.
So at resting potential, when the neuron is quiet, it's around minus 70 millivolts.
저단다 ene 완자 타본 코란 처음에 봤다 ene 예수 갑라 가르스나 코란기 다 ene 자메키미 누바스기도 자메키미 톱체스기도 하더라 자메키미 톱체데 ene 다 모던 든주 밀리볼트 모던 든주 도이레스.
This is the resting membrane potential right here.
저단다 ene 단다 파리디간라 땡기도 코 자메키미 톱체데 가르스나 다 ene 밀리볼트 모던 압주 다 두주 도와 인서다.
What happens when the action potential occurs? What happens to the membrane potential?
저단다 ene 레직 톱체 ene 춘드 참바 ene 기모기 톱체라 기로 가르도 그래. 기모 톱체. 레직 톱체 춘드 참바 기모 톱체 기로 가르도 그래.
What do you see right here on your paper?
저단 파리 들었다더라.
Just describe that to me.
It becomes more positive.
Okay. Does it become positive above zero?
Yes.
Okay. And then what happens?
It goes back to negative again.
It goes back to negative again. It gets even more negative.
And
then it comes back to normal. So it goes more positive. It goes past zero. And then it goes negative again. It goes past where it was. And then it comes back to normal. So there's 3 phases. 1, 2, 3. Does anybody have an idea how that might occur?
So the potassium ions leave the neuron, but then come back again.
Well, let's think about that. So potassium ions leave the neuron. What would that do to the inside of the cell versus the outside of the cell? Would that become more negative or more positive?
Negative inside, more positive outside.
Yeah. So this is more positive inside, not more negative. So let's just talk about phase 1. What could cause phase number 1?
So it's the phase where potassium gets inside?
No, potassium has already left. We have a membrane potential. I want to go from here up to here. How do I do that? How do I make the inside more positive? Let me just write down here exactly what's going on.
maybe sodium goes inside. sodium 들어와. 목이 놓고 그다음에 sodium 부재된 그 나로 용바이나 근데 포시쳐 자루라.
So this is the inside is negative.
저다 이네 원자 저거 나로로 있는 모시쳐 왔지.
And this is here, the inside is positive.
다디 간로도 참바에네 원자 저공이 나로데네 포시쳐 자루 그랬어.
So how do we get the inside from being negative to being positive? Somebody said something about sodium.
Sodium, yeah. He said it's the phase where when sodium comes in.
Okay, so if sodium came in, what will happen? The positive sodium is what kind of charge?
Positive.
And it brings positive charge inside. So this could be sodium coming in. Sodium enters cell. All right, during the tea break, I want you to think about this phase, number 2.
After the tea break?
Yeah, during the tea break.
During the tea break.
I want you to think about it, and after I'm going to ask you how this could occur. All right, and so I'll see you at 10 o'clock.
주발로 투용 쇼스.
대체체.